In this video, we're going to be talking about the research paper associating the randomized Bluetooth MAC addresses of a device. First, before diving into the paper, let's review a bit of context about how Bluetooth works. Most of your personal devices have Bluetooth. Your iPhones, Android phones, AirPods, and Apple Watches all use it for wireless connectivity. Bluetooth works by continuously broadcasting radio signals with unique identifiers, allowing devices to discover and connect with one another. But the problem is that if these identifiers aren't randomized, they can be exploited to track devices, since anyone can listen in on those signals. In practice, devices like the iPhone tend to always be emitting these signals, whereas Android devices are less likely to advertise themselves constantly. For example, if you check your phone's Bluetooth settings in a busy area, or if there's a lot of people, you'll notice that there's a lot of devices that are actively broadcasting, and most of them are probably Apple devices. Tracking Bluetooth devices is really useful for researchers who want to understand how people move around inside buildings and public spaces. It's a non-intrusive way to do mobility analysis, and unlike cellular signals, which are encrypted and hard to work with, or Wi-Fi signals that can be irregular, Bluetooth sends out packets at regular intervals. And this consistent broadcasting means that you can track a device's movement accurately over time. In other words, Bluetooth tracking lets you learn about how people move around, which is really useful for designing better buildings and city planning. But to preserve user privacy, the Bluetooth standard requires that devices update their MAC addresses at least once every 15 minutes. This means that a device's MAC address is intentionally randomized so that a fixed identifier of the device isn't continuously being broadcasted out. And that's where this research paper comes in. This paper investigates whether, despite randomization of MAC addresses, it's still possible to reliably link together the different MAC addresses a device uses over time, essentially enabling mobility tracking again. So this slide illustrates the core idea of the paper. Here you'll notice that there are 3 devices, each with their own MAC address. When the orange device changes its MAC address due to randomization, you can see that the previous MAC address disappears from the system. That's the key concept that makes this work. We assume that when a device randomizes its MAC address, the old one disappears and a new one appears. And by pairing these MAC addresses together, we can infer that they belong to the same device. But this strategy relies on the strong assumption that devices remain within the monitoring area during the entire observational period. In other words, when you see a new MAC address, it's due to the randomization rather than the device leaving the area. And that allows you to link the old MAC address with the new MAC address together. But there's a problem. So what if there's a lot of devices? Say there's over 100 devices. In this type of environment where there's a lot of devices, it's no longer trivial to connect devices. It's no longer trivial to connect the old MAC addresses, the disappearing ones, with the new appearing MAC addresses, because you end up with ambiguity and conflict clusters. In this slide, you can see that these 2 MAC addresses are disappearing, and then these new MAC addresses are coming into the system. So it's no longer ambiguous like in the previous slide, where each MAC address is connecting to one another because they're all happening at very different times, except for these 2. But in this new sort of system, you have these MAC addresses, and then there's not a trivial way to tell whether these devices, these MAC addresses are paired with one another, because the randomization is happening from both devices at the same time. And that happens a lot more when there's a lot of devices within the system. And we call this sort of thing happening, we call this conflict clusters. So a conflict cluster is basically a group where multiple disappearing MAC addresses could potentially match with several appearing ones. And that creates this ambiguity where it's unclear which new MAC address should pair with which old one. And this is crucial to figure out because we want this to work even in crowded environments and we want to accurately associate the randomized MAC address to the same device. To resolve this, the researchers came up with the notion of weak identifiers. So a weak identifier is essentially a characteristic of a device that isn't unique on its own, but helps group similar devices together. For example, aspects like the device brand, the type of advertising packet, or the duration between advertising packets can all serve as weak identifiers. And in this paper, the researchers use the duration between advertising packets as their weak identifier. And in using this weak identifier, you essentially group the devices that are similar to each other into a group. And then what this does is it reduces the matching space. So essentially you'll have less occurrences of this conflict cluster happening because there's less devices within in a single group, and then that means that there's less ambiguity for which MAC addresses should match with another MAC address. So what makes a good weak identifier? Well, there's three main things. Firstly, it has to be stable over time, and that means that it has to remain consistent for a given device even if the MAC address changes, and that ensures that it's reliable in association and as well as tracking. And secondly, it has to be sufficiently discriminative. And what that means is that while the weak identifier doesn't uniquely identify a device on its own, it should vary enough between different devices so that devices can still be grouped into smaller clusters. And finally, we want the weak identifier to give a uniform distribution. And that means that the values should be relatively evenly distributed across the device population, preventing too many devices from sharing the same identifier. In this paper, the duration between advertising packets serves as a weak identifier. The stability and measurable differences allow the huge group of devices to be broken down into smaller and more manageable clusters for association. When a device broadcasts Bluetooth advertising packets, it does so on a set schedule that's defined by a fixed interval and a small pseudo-random delay, and together these form T advertise. Since this timing is determined by the device's hardware or firmware, T interval, that's the fixed amount here, remains pretty stable even if the MAC address changes. And therefore, if you see two different MAC addresses with the same T interval, it's a strong indication that they probably belong to the same device. And when it comes to the math behind the paper, the authors developed a model where the observed interval between packets, T and packets, is defined by this equation. This allows them to account for situations where some packets are missed by the tracker. And from that, they can derive T interval, the fixed value, even when not every packet was captured. We won't be able to go into the full mathematical details in this paper since it's a little bit out of scope and more complicated. But the key takeaway here is that the equations enable a quantitative match of the timing characteristics across MAC addresses, and it allows the algorithm to correctly associate them to the device. In large environments, you might have many devices that change their MAC addresses around the same time, and that creates the conflict cluster that we talked about. So to resolve the conflict clusters, the proposed algorithm compares the T interval values associated with each MAC address, and then works to minimize the difference between these values when comparing the old MAC addresses with the new MAC addresses. Essentially, what it's doing is it finds the pairing that best preserves the device's inherent timing characteristics, ensuring that each disappearing MAC address is correctly matched with its corresponding new MAC address, even when multiple devices are changing at once, because with the multiple devices, in theory, they should be identified differently by the weak identifier. Otherwise, we would still have that ambiguity. But that's why choosing a good weak identifier is very important. So this is the experimental setup. that the researchers tested their approach with. They used 3 scenarios. The first one is an environment where it's highly controlled and it's only 6 devices over 40 minutes. The second and third ones are both uncontrolled environments, where setup A is a very heterogeneous environment with over 1,000 devices, and then setup B is another uncontrolled environment where there's about 50 devices, but then they remained in the range the whole time. So there's no devices that are entering or leaving the system. Performance results show the algorithm achieves low mismatch rates, under 5% in setup A and 10% in setup B. What the researchers found is that the method works significantly better when there's fewer devices in the area and also in a static environment where devices remain in range for a long period, such as a park. In these settings, the pairing of disappearing and appearing MAC addresses using the weak identifier is highly reliable. However, in highly dynamic settings where devices are frequently entering and leaving the monitored area, the system struggles to maintain the same level of accuracy, resulting in higher error rates, up to 10%. Essentially, the method performs best when there's stable population of devices, and its performance degrades as the environment becomes more chaotic and there's more people leaving and entering. So that brings me to potential improvements for the paper in future work. And as I was saying, while the method works well in stable environments, it fails in dynamic settings, such as transit stops or storefronts, where devices frequently enter and leave. And that comes from the assumption that MAC address changes is due to randomization rather than movement, so it doesn't work in those cases. And another limitation of this paper is in using the advertising interval. So the advertising interval likely comes from the hardware that determines it, and if all the devices are the same model of device, then they're likely to have a very similar advertising interval, and that essentially will remove the fact that the advertising interval serves as a good weak identifier because it no longer breaks up the large group into several smaller groups. And to improve upon this, we could possibly introduce additional weak identifiers, such as the RSSI value, which is the signal strength coming from the Bluetooth device, and that gives you an indication of how far away the Bluetooth device is, which should be able to tell you how should be able to give you a decent differentiator for different devices, as long as we incorporate that with tracking. So we could also detect whether a new device is an actual new one or whether it's just changing MAC addresses. And by handling that case, then it'll improve tracking accuracy where the environment is a highly dynamic one. So in summary, this paper demonstrates that even with randomized Bluetooth MAC addresses, it's still possible to associate different MAC addresses from the same device by leveraging the stable timing between advertising packets as weak identifiers, given that it's a very heterogeneous group of devices. The algorithm, although it's not perfect, can effectively track devices even with the randomization. And future work can refine this further by exploring better weak identifiers and more experimentation on different environments as well.